So as part of, I mean, it's part of the unit, actually, selecting procedures, but it's also part of our review for this test. And I really like the opportunity to go back and try to fill out all this with just from memory. Because eventually that's where we need to be, right? And I'll show you mine. I wanted you to fill it out a little bit more in depth than just names. So, and I forgot to write the power rule on here, so I'm going to do that now. D dx of x to the n is n x to the n minus 1, like that. Anyway, that's a lot, right? If you just glance at it, there's a lot of things we've learned about how to take derivatives. Some of the bigger ones that I would say, in terms of needing to just brute memorize, because some of these I think just become automatic, like constant, right, at this point. Same with constant multiple. We know we can just pull that out front. I think the power rule probably by now is pretty automatic. But the quotient rule, it might be getting pretty automatic, but it's definitely one where you can mess up, right, if you're not careful. We had already talked about these being ones that we don't use as much, so it's hard to remember. I do want to give you a memory aid for them, though, and specifically like a to the x and log base a of x. If you can memorize the e ones, knowing like derivative of e to the x is e to the x, it helps because it follows the same format as a to the x natural log of a, but natural log of e is just 1. So I think that kind of helps to know you have to stick that natural log of the base at the end. And then same with log base a of x. It's the same as log base e. That's supposed to be an e right there. There we go. That's not what I meant to write. Something looks weird about that. No, it's good. Never mind. It's the same as that one, except instead of natural log of e being 1, we have to write the natural log of a underneath there.
So there's some difference. One is that you're just like a polynomial, so you have like x squared plus x plus.
Well, that, yes, but also like if we had, let's say 3x squared plus natural log of x, even like that. That's
making sure they're separate.
Yeah, so just treating them. I put just split up as a reminder that we can treat them separate, like you said. Good. Okay, so those were a couple, I think, if you just look at them a few times, and again, this is something that you'll probably want to, in my opinion, as we get further and further along, you'll want to put this somewhere in your notebook where you see it and reference it often, so it gets really locked in. Sine, cosine, I think we're good on, but tangent and cotangent we haven't done as much. So secant squared, negative cosecant squared. One theme that we've seen is the c's are negative, which is helpful, like cotangent was a negative cosecant, and then over here all the c's were negative. Okay, derivative of secant x and cosecant x, those ones we definitely haven't used much. So just keep looking over them, try to get it locked in. Secant tangent, I think it seems to follow. You know, like secant tangent versus cosecant cotangent. To me, those go together. You just stick a negative sign out front. So that was all chapter 2. Again, some of those we used a whole bunch, some very little. But all of them either could be used or will be down the road, right? Okay. And then in Unit 3, the first thing we start out with is the chain rule. And I want to talk to you about how I'm writing my notation and see if that's something you might adopt, if it's helpful. And it just goes back to the way I learned this, and it flows, for me, it flows like v du plus u dv. So v and u being the first, second and first functions respectively. Same here, v du minus u dv over v squared. So you'll see in a lot of my work that I go and label things u and v. And like for the chain rule, for quotient, sometimes I'll do that, not as often. So speaking of chain, df du, du dv, dv dx. And it just makes that so much more clear. Okay? Okay, then we did implicit, which is more of a process, right? It's not just a rule like these kind of were. It was more of a process of isolating dy dx algebraically. And then we got into the weird ones, probably the weirdest ones that we've done, which is all these inverse ones. How are you doing on memorizing all the inverse trig ones?
That's one on the big one. See, they're so similar.
Yes.
Like all of them. There's just like minor differences.
Yeah, I agree.
Yeah.
I don't know how memorization works for you guys, so repetition. I suppose maybe one of these days I could just hand you, or not even hand you, just say get a blank piece of paper and write this, like recreate it, you know, and maybe the actual studying for that. I don't know. Let's see how we feel today. I'd like to because it's the long day.
Yeah.
And this is a long test. It's not a long test. It just takes a long time. There's 23 questions, I think. 22 or 3. So we'll see how it goes. I think we'll be okay. So, how'd yours look compared to this? Did you forget any? Did you?
Well, so I kind of just put it down. I did, like I just like the big ideas. Like that whole dy, d, like it was all for the inverse. I didn't know anything.
Okay. And so the more times you can write it and write it and write it and write it, the act of writing creates a visual stimulus to your brain, which is more than just hearing it, right? So anyway, it's a good thing to just write and rewrite. I found it helpful. I had to go back and look up these, the secant, the tangent, cotangent, and the secant, cosecant. I didn't remember those. So I felt like it was a good review for that. Anyway, if you look through the problem set for that, it would function as a good review itself. These are kind of small, but it's kind of helping you just narrow down each problem has you narrow down from that list which ones to use, especially now that we're kind of at the end of all the derivative processes. It's some of the work is not even just memorizing them, but knowing which one to pick, right? So let's kind of quickly talk through, not necessarily do each one, but let's talk through strategy as a quick review. So find the equation of the tangent line for that. What, out of that big list that we had, what process are we for sure going to need on that?
And implicit. Yeah.
Power rule, good. And implicit, how do we know it's implicit?
Because you have X, Y,
Yeah, this is an implicitly defined function with x and y together. So we would do 18x plus 32y dy dx, and then what about that side? 0. And then get dy dx by itself and plug in the point to get your specific slope. Good? Okay. Next one. What's the slope of this tangent line? What is the process? In fact, let's even write out the derivative there. These ones they can be subtle, and then it's easy to miss stuff, right? Okay, what was it? What is arc? Inverse. So we know it's going to be and so I don't know if this is helpful, but I would write this myself. I would rewrite this as inverse that way because personally I don't like arctan as much. And this is where I would put a u in there, and then off to the side I would say u equals 2x. Okay, and then this is dy dx, dy du times du dx. Why do we have to do both?
Well, because you have to relate it back to X.
And this is a chain rule problem, right? Okay, So then I would write 1 over x, well, let me write it out fully. 1 over u squared plus 1 times d dx 2x, something like that, okay? And then substitute u back in, 1 over 2x squared plus 1 times the derivative of that, which is just 2, and finish up. Does that make sense? That's how I like to do these. I'm not saying you have to, but I find the organizational structure helpful to not miss stuff, especially when these get long. And then we'd plug in a half, and a half squared would be a fourth, so the bottom would be 2, and then we would get our slope as 1. Good? All right, how about this one? What rule should we use on that? What was it? Sorry.
Quotient rule.
Quotient rule
Power rule.
and power rule. Good. Remember the quotient rule does have that b squared, that low squared on the bottom. So sometimes that makes a mess. Okay, how about that one? And how have we handled the derivative of a square root? It's really power, right? So again, this would be like df du times du dx, where u is 1 plus root x. What about that? Is that also something? Yep, so this actually should have du dv dv dx, like that. So if we go fill this in, we're going to differentiate this first radical. So do you guys remember the differential of that, or the derivative?
1 over 2.
Yep. Good, and then we're going to differentiate this one, which is what?
1 over
Times 1 in this case. Okay? And then we would substitute that in there and that in there. Do you find that helpful to write it out? Okay. Alright, so similar to the very first one we started talking about, how do we know if a tangent line is horizontal? Yes. So dy dx equals 0. That's what we're looking for. So we would do the implicit differentiation again and set what equal to 0. Right, I know, but that has two pieces, right?
Oh.
Or it could. Will this one? Here, let's just do it real quick. So 2x plus 8y dy dx equals 0. So, yeah, this one does. So subtract 2x and then divide by 8y.
Oh, well, then you would have to say your numerator equals 0.
Yeah, that's what I was saying. Good job. Which one of these do we set equal to 0? The numerator. Yeah. So that would be at A. Okay? Well, what does it mean by determine the number of points where that's true?
Well, if it was like a polynomial, you could have multiple points.
Yeah,
X
so
equals 0.
So we set the numerator equal to 0, which tells us x. This is at x equals 0. Then what do we do to get those horizontal asymptotes? Because I could see you just doing that. Not you guys, I'm saying I could see the problem to stop at that, but that's not the question, right? So what do we do? Okay. Yeah. Set that equal to 0 and solve this guy.
It would solve for everywhere that y equals 0.
So we get y equals plus or minus 2. Okay? So this is 2 different places where that happens. That's a weird question. And what?
I said I would have said one.
Yeah.
Like just off the top of my head.
Yep. So this is a circle, so it would have 2 places.
Yeah.
But yeah, that's a tricky problem for sure. How about that one? That's a mess problem.
Yeah, it's like product rule, chain rule, and power rule.
Basically all of them.
Yeah.
The A to the X.
Yeah.
Yeah, that's a good one. And if you look at the answer choices, you can see that it becomes kind of a mess. Maybe we'll look at that one for a good problem to do. All right, I think we're kind of getting the idea. This one, what rules are being used there?
Oh, your arc sign,
Okay, so arc sign.
and then your product, or wait, yeah, product rule.
Sort of. It's really the constant multiple rule.
Oh, yeah.
So we could just pull the 2 on that one. So constant multiple.
Right.
This one is inverse trig. And then this is sum, right?
Yeah.
And then this is power. That's a lot going on. It's definitely easier than the other one, but any other good ones on here? No. All right, so if you think of what we just looked over as test questions, that's kind of the idea. Let's say it's 23. I'm pretty sure it's 23 questions. 20 of them are multiple choice. Okay?
And the rest are.
The other 2, or the other 3 are 1 question FRQ, 1 question FRQ, and then a 4 question FRQ. You know, the full work it through.
Yeah.
They're not horrible. Those FRQ ones aren't bad. Honestly, there's a lot of work that goes in, just like these would be, a lot of work that goes into the multiple choice questions. Some of them. Like I said, like this would be. Like this, how long would that take? Probably 2 minutes maybe to do, right? And that one up above that we said was kind of nasty would probably be 3 or 4 minutes. So the multiple choice, I think, is a bigger deal on this particular test. But it's like this, like, you know, maybe it's write the equation or find the slope of, or what's dy dx and do the implicit, something like that, right? Or just find a plain old derivative of some kind of combination of properties. That's kind of how that looks. And then we have one more thing to talk about, which I think you'll pick up pretty quickly. It's that higher order derivative stuff. Do you remember that? So let's do that right now, and then we'll see how you feel about it, and then we'll talk more about the test. So this is 3.6, last section. And this is just notation for higher order derivatives, depending what we have in terms of y's, f's, or Leibniz notation. And as we get out to this, obviously we're not going to just make 15 tick marks or whatever. So we can do, in parentheses, do our derivative count. This one, I do want to make note that the order is different for the numerator and denominator. In other words, in the numerator, the derivative count is on the d, and in the denominator, it's on the variable. Okay? So when I don't know I suppose we could find out, but if you were doing an FRQ and wrote that notation wrong, they might take a point off for that. So, guys, the big idea with just doing higher order derivatives is to take the derivative of the derivative. That's really all it is. So they can be, like on this first one, they can be kind of fun, I think. And hopefully you see that that does mean that they have an end point, right? Well, unless it's like e to the x, I guess, something like that. So take the derivative of the derivative. What would be f prime of this? Right? It's 6, you know, I don't know. Okay. Then we just take the derivative of that and take the derivative of that. So why don't you run through that, just a good little review of the power rule. Good on that? Okay, suggestion on these kind. Rewrite with exponents. So x to the 1/2, and while the other one is fine, plus x to the -2. And then as we take subsequent derivatives, it's easier to deal with those exponents. So this becomes 1/2 x to the -1/2 plus -2 x to the -3. And if you had to stop right there, I mean, you could simplify it back to radicals and positive exponents and pick your choice, but it does make this part a lot easier. So now we'll do the power rule again and get -1/4 x to the -3/2 plus 6x to the -4. Then, like I said, at that point, if we needed to, we can rewrite. Do you guys remember the rational exponent to radical connection?
But could you just leave it like that? Like, do what you
If it was an FRQ, sure. But if it was a multiple choice, you might have to convert back. But it makes it faster to take the derivative. So what goes in our index right here? Nope. It's the 2. It's the denominator.
Oh yeah, because that's like your 1/2, which makes the square root, and then the 3 is your
Yep.
exponent.
But where's the negative go?
It's the negative made it be in the denominator.
Oh, okay.
Yeah. Anyway, that one we'll just do 6 over x to the 4th. So it could look like that as well. All right, so that's concept of higher order derivatives. Let's look at use with implicit differentiation. And this is kind of the bigger idea of where we should focus. You want me to wait for you?
No, I'm just listening.
Okay. Let's work through this problem as an example because it's kind of hard to tell you without showing you how this looks. So we have this implicitly defined function, so we need to find the implicit derivative. So, how do we do sine? Cosine. And then we'll get 1 dx over dx, which we can just leave, plus 1 or just dy dx. Good?
Would your cosine y also be multiplied by dy dx?
Oh, yeah, I forgot that part. These are huge now. Cosine y, dy dx. Good job. Okay, and then we want to get those dy dx's together. So this is that part where you factor it out, except don't factor it completely out of the cosine, right? I mean, I said that weird. If it's inside, don't do it. That's what I was trying to say. In this case, it's okay. Dy dx cosine y minus 1. And then just divide. Okay, so that was derivative 1. What do you think we do for derivative 2? So now we're going to go do the derivative of this guy. So we took the derivative of the left side essentially just by adding the 2's in there. What rule do we have to use on this? Quotient rule. So you can write it out, but if we do low d high, what's the derivative of 1? That's just 0, right? So low d high is just 0. If you want, write it out. In fact, let's do just to be safe. Minus high d low. So I'm not going to write the 1, but what's the derivative of the low? And I would recommend putting a bracket or a big parenthesis so we track the whole thing. So low d high, we're done, that's 0. High d low is 1 times negative sign. Good.
I remember this problem last.
You do this specific
No,
thing?
like doing this because we always kept getting. So like with me, I have negative 1 times 1 over, or 1. Oh my gosh. Dy dx equals negative 1 over 1 minus cosine y. Instead of cosine y minus 1 because of how I like moved it around, I guess.
Okay, which is the same. You said negative 1 over the reverse of this. Those are the same.
Are they?
Yeah. Yeah. And I think this is what you said, right?
Yeah.
Yeah, because if I factor out a negative 1 here, this becomes negative and that becomes positive, and then it cancels up here and makes that positive. So they're the same.
Oh, you just have a positive 1 on top. Okay.
Yeah,
Never mind.
you're good. Anyway, let's kind of clean this up a little bit.
Yeah, it's also over.
Yeah, I forgot to write that part. Cosine y minus 1 squared. Okay. All right. So do you see the kind of weirdness at this point? What is it?
There's a d squared, or like the second derivative and also the first derivative.
Yeah, there's both in there. We have this dy dx floating around in the numerator. So what we do there, yes. So just substitute that expression in. Okay? And then it's not sine of that, so we can manipulate this if we want to. What could we do with this numerator and denominator to help clean this up a little?
Put the sine y in the numerator.
Yeah.
And the cosine y minus y squared denominator.
Well, but what will it be when we bump this down here?
Cosine y minus 1 to the third.
Yeah, good. Okay, if this was an I was going to say in context problem. What I meant was like if we had to find the value of the second derivative at a point, now we could plug in, we could obviously plug in here, but we could have plugged it in here as well. Okay? Or we could have found the value of the slope over here, or dy dx I mean, and then plugged it even in there. So sometimes those save you a little work if you don't want to go symbolic the whole way through. Okay? Any questions on that? Okay. What happens when you repeatedly take the derivative of e to the x? It's just the same, right? E to the x, e to the x. Now that one has the product rule too, but it stays the same. Okay. So let's kind of talk plan.